You know, it's interesting when you think about the technology that keeps things running smoothly in our daily lives, like the air conditioning in your car, or, say, the big refrigeration units you see in supermarkets, even really high-efficiency industrial cooling systems.
Yeah, those massive systems.
Exactly. And they all rely on these incredibly complex aluminum heat exchangers. And often, the entire lifespan of that machinery, we're talking millions of cycles, can come down to just one tiny, almost microscopic seam.
It really can be the Achilles heel, like you said, that single joint.
So our mission today is a deep dive into exactly that potential weak point. We're looking at the structural integrity and, crucially, the fatigue life of aluminum brazed joints, specifically in microchannel heat exchangers, or MCHEs.
Right.
We're going to extract the core insights from a very rigorous recent study. They use quite a range of techniques: physical tests, digital modeling, microscopic analysis, basically trying to figure out definitively why these seams fail under constant stress.
And it's critical research, because these systems, they absolutely demand maximum efficiency and, just as importantly, maximum durability over years and years.
Yeah.
The components themselves are usually built from aluminum alloys. Typically, you see the 3XX and 4XX series.
Why those specifically?
Well, they're chosen for a combination of things. Really low density, which is great for weight. Excellent thermal conductivity, obviously key for a heat exchanger.
Right.
And, pretty satisfactory strength for the job. They've become the benchmark for a lightweight thermal transfer.
Okay. And the method used to join all these intricate aluminum parts is brazing. We should probably clarify that a bit, shouldn't we?
Yeah, good point. Brazing creates a permanent metallic bond. You use a filler alloy. In this specific case, it was a 4XX series aluminum paste.
Okay.
This filler melts at a high temperature, yes, but still significantly below the melting point of the actual components being joined.
So it's not welding where you're melting the base metal itself.
Exactly. Not welding, and definitely not soldering, which happens at much lower temperatures. Brazing is really the preferred method for these complex MCHE assemblies.
Why is that? What are the advantages over, say, just bolting them together or trying to weld them?
Well, compared to mechanical assembly or welding, brazing gives you superior sealing, essential when you're dealing with high pressures.
Right. Can't have leaks.
Precisely. It also minimizes overall thermal distortion because you heat the entire component uniformly in a furnace.
Ah, I see. Less warping.
Oh, less warping, yeah. And it provides really reliable strength. Honestly, this process is what made modern, compact, efficient refrigeration possible.
There's always a but, isn't there?
Yeah.
Here's the major challenge this research tackles and why we're doing this deep dive. Despite brazing being the industry standard for, decades, the actual structural integrity of these joints, especially when they're subjected to relentless, complex cyclic loading.
You mean like the pressure going up and down constantly?
Exactly. Think about the compressor in your fridge or AC, kicking on and off millions upon millions of times. That kind of loading. The integrity under that condition is surprisingly a scarcely addressed scientific and engineering concern.
That's absolutely right. We kind of know intuitively the joint is the weak link. It has to be, right? I mean, it's where you have this mix of materials, the base metal, the filler metal, what we call metallurgical heterogeneity.
Okay.
And you combine that with complex geometry, little corners and edges. This mix inevitably introduces local stress concentrations.
So spots where the stress gets amplified. Exactly.
And those spots are precisely where cracks love to start, especially under fatigue. So for engineers designing systems meant to last, 10, 15 years or more, really understanding how this joint behaves under cyclic stress is paramount.
Okay, let's unpack the study then, kind of step by step. Before the researchers even looked at the finished joint's performance, they had to figure something else out first.
What was that?
They needed to understand what the intense heat of the industrial brazing process itself, that whole thermal cycle, peaking near, 600 degrees Celsius.
Okay.
What that does to the component materials before the filler metal is even involved.
Ah, so isolating the effect of just the heat. That makes sense. They did this by running tensile tests on the materials in two states. First, as they came from the supplier as received.
Okay.
And second, after putting them through the exact same industrial thermal cycle, peak temperature, time, everything, but without applying any filler metal, they called this the heat-treated condition.
And the specific components they looked at were the headers made from a 3XX series aluminum alloy.
Right. Those are typically made by lamination or rolling.
And the tubes, these multi-port extruded or MPE tubes, also aluminum.
Yeah, and those, as the name suggests, are made by extrusion, forcing the metal through a shaped die.
So two very different manufacturing histories right there, rolling versus extrusion. That creates fundamentally different starting microstructures in the metal.
And this is where it gets really interesting. What they found was that the thermal cycle had the completely opposite effect on the strength of these two base materials.
Opposite. How so?
It clearly showed that the way the material was made before brazing rolled versus extruded dictates how that alloy reacts to the heat treatment.
Wait a second. You're saying the heat made one material stronger and the other one weaker. That feels counterintuitive. I always thought heating metal generally softens it.
Well, that's often true, yes, but it really depends on the metal's starting condition, its history. Think about the rolled header material first.
Okay.
It starts out in what's called a cold worked state. That means the rolling process itself has strained and kind of disorganized the internal crystal structure, the brains. This actually makes it stronger initially.
Right, work hardening.
Exactly. But then when you hit that cold worked material with the high heat of the brazing cycle, around 600 degrees C for a few minutes, you trigger processes called recovery and recrystallization.
So the heat basically lets the stressed grains relax and reform into maybe softer, less strained grains. It kind of undoes the hardening.
Precisely. You've got it. The rolled header material suffered a really significant reduction in strength. We're talking maybe a 15 to 20% drop in its ultimate tensile strength.
Wow.
So the thermal cycle substantially softened it. It became less robust even before the joint was actually made.
Okay, so that's the rolled header. Now, what about the extruded tube material? How did it manage to gain strength? That's the surprising part.
Yeah, the extruded tube material, which has a different starting microstructure, more fibrous, already strain hardened from the extrusion process itself, it just reacted differently.
How?
For this particular alloy and structure, the heating cycle seems to have actually stabilized the microstructure. There might be some diffusion effects, maybe some precipitation phenomena happening on a tiny scale.
Meaning trace elements moving around and pinning things?
Yeah. Sort of like that, yeah. Hardening the matrix slightly. The bottom line is, it showed a modest but definitely measurable increase in strength after going through the thermal cycle.
That is hugely relevant for anyone designing these things.
Yeah.
If you're listening, this means the final strength of your heat exchanger isn't just about picking the right alloy from a data sheet.
Not at all.
It's also fundamentally tied to whether that part was rolled or extruded before it ever saw the inside of a brazing furnace. You have to account for one key part getting weaker while another gets slightly stronger.
It introduces a massive trade-off in the design process. You know, if you rely too heavily on the initial as-received strength of that rolled material, you have to remember the brazing process is going to knock it down significantly. So you might need to make that part thicker, heavier, just to compensate. The thermal history is truly half the battle here.
Okay, so once they understood how the heat affects the base metals individually, the next logical step is, where does the whole assembly actually break? They knew the joint was the likely culprit, the weak spot. But where exactly does that crack initiate when the heat exchanger is cycling pressure millions and millions of times over his life?
And they tackled this scientifically, which is important. They didn't just guess based on field failures, although that informs it.
What did they do?
They built a simplified physical prototype, MCHE, first. Then they put very precise strain gauges on critical locations.
To measure the actual strain distribution.
Exactly. And they used those real-world measurements to validate a detailed finite element analysis, or FEA, computer model, essentially creating a digital twin of the joint region they could trust.
Okay, so they have this validated computer model. What did it tell them about where the stress was highest?
The FE model really zoomed in on the geometry of the joint itself, specifically where the filler metal, which typically forms a little rounded corner or fillet, where that fillet meets the base metal of the tube wall. And importantly, they modeled this junction using a deliberately conservative assumption.
Conservative meaning, like worst case scenario.
Pretty much. They modeled it with a simplified geometry that featured a sharp edge right at the fillet toe.
Okay, fillet toe. Can you break that down? Where exactly is that?
Imagine the bead of melted filler metal that joins the tube to the header. The toe is the very edge where that bead stops, right against the flat surface of the tube wall.
Got it.
In reality, you hope it's a smooth, gradual transition, but any tiny imperfection, maybe a bit of flux residue, or just how the metal flowed, can create a little notch right there. The model assumed the sharpest possible corner imaginable at that spot. Engineers call this a stress singularity.
A stress singularity.
Yeah.
That sounds intense, like infinite stress. Is it just the mathematically sharpest corner they can put in the model?
That's a good way to think about it. It is a geometric idealization, yes. A mathematical point where the stress theoretically goes to infinity. Now, obviously, real materials can't sustain infinite stress.
Right.
But the location of that singularity in the model tells you exactly where the stress concentration will be highest, and therefore most critical, in the actual physical component. It points to the hot spot.
And did the model clearly point to one specific location?
Absolutely, without a doubt. The simulation showed a critical concentration of tensile stress, pulling stress right at that theoretical sharp edge, specifically at the toe of the brazed fillet, and even more specifically along the lateral edge of the MPE tube.
Okay, so not just anywhere on the toe, but on the side edge of the tube where it meets the fillet.
Precisely. This finding was crucial because it told them exactly where to focus their subsequent fatigue tests. No more guessing.
So that FEA work then guided the physical testing phase. They designed a special fatigue specimen that accurately replicated this critical joint geometry and, importantly, the stress field identified by the model. Then they started hitting it with cyclic loads.
Right, uniaxial cyclic loading. Pulling and releasing, millions of times. They used a standard stress ratio, R equal 0.1, a frequency of 20 hertz, and their target was 10 million cycles. That's often considered the threshold for effectively infinite life in these kinds of applications.
10 million cycles. And how did they determine the actual fatigue limit?
They used a specialized testing procedure called the staircase method. It's designed to efficiently zero in on the stress level, where roughly half the specimens will survive those 10 million cycles and half will fail.
Okay. And the result, what was the limit?
The estimated nominal endurance limit for 50% survival probability at 10 million cycles was found to be 60 megapascals, or MPa.
60 MPa. Now, help us put that number in context. You mentioned the base materials might have strengths closer to 90 or 100 MPa, maybe more, even after the heat treatment. 60 sounds quite low in comparison.
It is relatively low, yes. And that's the whole point, really, that 60 MPa represents the maximum range of cyclic stress that this joint can handle, essentially indefinitely without failing.
So in the real world, if a heat exchanger in, say, a commercial chiller operates below that stress level at the joint toe, it should theoretically last for that 10 million old cycle target, which could easily be 10, 15, maybe more years of service.
Exactly. But the fact that this endurance limit is so much lower than the strength of the base materials themselves confirms the critical point. The joint, with its inherent geometric stress riser at the toe and its mixed metallurgy, is absolutely the dominant factor controlling fatigue life.
The base material can be super strong on its own.
Doesn't matter as much.
But the joint itself sets the ultimate limit for the whole component's lifespan under cyclic load.
That's the takeaway. It's the fatigue critical region.
Okay, so the simulation predicted the failure spot. The fatigue test confirmed the joint is the weak link with the specific endurance limit.
Now, let's get to the microscopic evidence. The smoking gun, perhaps?
Right. They used scanning electron microscopy, SEM, to look closely at the fracture surfaces of the failed fatigue specimens. Fractography. And did the physical evidence line up with the computer model's prediction? Did the cracks actually start where the FEA said they would?
Absolutely, perfectly. The physical evidence was entirely consistent. Crack initiation was consistently found exactly where the simulation predicted, right at the brazed joint toe, along that lateral edge of the MPE tube.
And critically?
And critically, yes. This location also matches where service failures have been observed in actual heat exchangers out in the field. So the lab work directly correlates with real-world experience.
Okay. And when they zoomed right in on those fracture surfaces, what did they see? Were there typical signs of fatigue failure?
Oh, yes, very much so. They observed the classic features you expect to see in high-cycle fatigue failures.
Like what?
Well, first, the crack clearly started right at the surface, which is typical when you have a stress concentration like that fillet toe acting as the trigger. Then, as the crack grew slowly with each stress cycle, you could see features often called ratchet marks or beach marks in the propagation zone. They look like tiny tide marks, really, showing the crack front advancing incrementally. And finally, the remaining material eventually couldn't take the load anymore, and you see a different texture in the final rupture zone, signs of a rapid overload failure, often ductile tearing in this kind of aluminum alloy.
Standard fatigue progression.
Yeah.
But there was something else, wasn't there? Something more intriguing found right near where the crack started.
Yes. This was perhaps the most critical observation from the fructography. Right there in the crack initiation zone, near the surface at the fillet toe, they consistently found small particles or inclusions embedded in the metal. They didn't look like the aluminum itself.
Foreign bodies, essentially.
Exactly. So naturally, they analyzed their chemical composition using energy dispersive X-ray spectroscopy, or EDS.
And what did the chemical analysis reveal? What were these tiny flaws made of?
The analysis showed they contained fluorine, F, potassium K, aluminium Al, and also cesium Cs.
Fluorine, potassium, aluminum, cesium. Okay, so what does that combination of elements tell us? Where would that come from?
That specific combination of elements is the dead giveaway. It's the characteristic chemical signature of the brazing paste, or more specifically, the flux that's mixed into the paste.
Flux. What's its job in the brazing process?
Aluminum naturally forms a very tough, stable oxide layer on its surface almost instantly. This oxide layer prevents the molten filler metal from properly wetting and bonding to the base aluminum.
So the flux is there to clean the surface somehow.
Precisely. The flux contains chemicals like these potassium and cesium fluorides that aggressively react with and break down that aluminum oxide film at the high brazing temperature, allowing the filler metal to flow and create a good metallurgical bond.
So finding traces of these flux elements trapped right at the failure initiation site means?
It means these inclusions, which they estimated to be around 75 to 80 micrometers in size. It's actually quite large on a microstructural scale.
Yeah, that's not tiny.
These are essentially manufacturing defects, remnants of the flux that didn't get fully consumed or displaced during the brazing process and got trapped near the surface in that critical high-stress zone.
It's like microscopic chemical contamination left over from the joining process itself.
Exactly. It's not just the stress concentration from the geometry, it's these pre-existing flaws, this trapped debris.
And these flaws acted as the trigger points.
That's a conclusion. They acted as preferential sites, like little ready-made defects, for the fatigue cracks to nucleate and start growing. The inclusion creates a local weak spot, maybe even its own microstress concentration, ensuring the crack starts there, probably long before the surrounding defect-free metal would have initiated a crack on its own. It's the ultimate trigger.
Wow. This study really paints such a complete picture, doesn't it? It connects the dots all the way from the initial manufacturing of the parts, through the effects of the heat cycle, down to the stress concentration at the joint, and finally pins it on these microscopic defects.
It really does. It's a great example of multi-scale analysis.
So let's try to synthesize the key lesson here for you, the listener. What this tells us is that the structural integrity, the real-world lifespan of these high-tech MCHEs isn't determined by just one thing. It's a complex interplay, a confluence, really, of at least four major factors. One, the original forming process of the base material, whether it was rolled or extruded, because that dictates how it responds to the heat.
Right, we saw that strength change.
Two, the overall effect of that brazing heat cycle on the base material strength. One gets weaker, one slightly stronger.
Yep.
Three, the geometry of the joint itself, specifically that fillet toe, which naturally concentrates stress.
The unavoidable geometric factor.
And four, and this seems maybe the most crucial takeaway from this particular study, these microscopic manufacturing defects.
Yeah, the flux inclusions. Finding those right at the crack initiation site really underlines the critical importance, the absolutely critical influence of strict quality control during the brazing process itself.
It means just perfecting the alloy chemistry or the overall component design isn't enough, is it? If the actual process of joining the parts together isn't clean and well controlled.
It can undermine everything else. Absolutely. Achieving good fatigue performance, especially in these high cycle applications where things run for years, demands obsessive control over the entire brazing operation. From surface preparation to flux application, heating, cooling, everything. Especially focusing on minimizing any incorporation of flux residue near the surface in those known high stress zones, like the fillet toe.
It's a stark reminder, isn't it? Even in supposedly clean, advanced manufacturing, tiny bits of chemical debris left behind can ultimately govern the lifespan of the entire component.
It really can. Process control is key.
Okay, this brings us to a final, maybe provocative thought for you to consider. The researchers, as we discussed, had to use that conservative FEA model with the sharp corner assumption, the stress singularity.
Right, the mathematical idealization.
Which means the true, actual, local stress value right at the microscopic point where the crack initiated on that flux inclusion.
Yeah.
Well, it's still technically unknown. The model points to the location, but the idealized infinite stress isn't the real number.
That's correct. It's the engineer's perpetual challenge. modeling reality versus the necessary simplifications.
So here's the question to ponder. If you could somehow perfect the manufacturing process, if you could achieve a perfectly smooth fillet geometry, eliminating that sharp micro-notch effect, and simultaneously eliminate those flux-related inclusion defects entirely, how much longer could these components truly last?
That's the million-dollar question, isn't it? We know the joint is the weakest link, but what is the theoretical upper limit of its strength? If you could remove these known flaws, the geometric ones and the material ones, its potential is still somewhat shrouded by the complexities and imperfections of current manufacturing reality.
It suggests the next big engineering breakthrough might not be inventing a radically new aluminum alloy.
Perhaps not. Perhaps it's really about perfecting the joint, mastering that critical interface down to the microscopic level.